Okay, so as in the last video, we have, discussed the example number 3 of Born-Haber process, right? We have discussed now in very detail and we have very good knowledge about Born-Haber cycle. Born-Haber cycle is basically a process in which you will initially convert your reactants into the gaseous form, and you're gonna make those both react together in order to produce 1 mole of ionic compound. Along with that 1 mole of ionic compound, the lattice energy would be released. And for calculating that lattice energy, we have Born-Haber cycle, right? Or you can say Born-Haber process. So Born-Haber cycle or process is used to calculate the lattice energy which is produced along with the 1 mole of ionic compound from the gaseous reactants, right? So what initially we did, we took reactants in their stable form, right? We didn't initially took them in the gaseous form. We initially took those reactants in their stable state. Now I need to make it into the gaseous form, right? So in order to make magnesium into the gaseous form, I need to give it heat of sublimation, right? So I gave heat of sublimation, then I need to remove 1 electron from the magnesium gaseous atom. So I know that ionization is the energy which is required to remove 1 electron from the valence shell from the gaseous atom, right? Then I need to take 1 more electron as well, since I know that the magnesium electrovalency is 2, right? So I gave another ionization energy and magnesium double positive was formed, right? Then chlorine is already in the gaseous form, but I need to make the break the bond between these 2 chlorine atoms. So in order to break the bond between these 2 atoms of chlorine, I have given energy of dissociation, right? Then now I have 2Cl in the gaseous form, but yeah, I don't want 2Cl in the gaseous form. I need 2Cl minus in the gaseous form, right? In order to make it negative, in order to make it gain an electron, I know that energy which is released when an electron is added to the valence shell of the gaseous atom, that energy is what we call the electron affinity. So electron affinity is released. Now basically I have reactants in the gaseous form, right? So these both reacted together, 1 mole of MgCl2 produced. Along with that, the energy which is produced is lattice energy. And to calculate the lattice energy, we have Born-Haber process. So this entire is what we call the Born-Haber process, right? This is Born-Haber process. In today's video, we are going to learn about Fazan'S rule, right? Before moving towards the Fazan rule, I need to tell you that no ionic compound is completely ionic and no covalent compound is completely covalent. What did I mean by this, right? What did I mean by this? For example, if I have an ionic compound, for example, if I have MgCl2, which I know that is ionic compound, right? But this is not completely ionic. Not completely ionic. Not completely ionic. There exist some covalent characters. There exist some covalent characters. right? Or you can take any example of covalent compound that would not be completely covalent. There would some characters of ionic compound exist, right? So there is no compound in the universe which is completely ionic or completely covalent. There are some characters of covalent compound exist in ionic compound, and there are some characters of ionic compound exist in covalent compound. All right, in order to find the covalent characters in the ionic bond, the rule which we use is Fazan's rule. So yeah, we have ionic compound, right? Here covalent characters exist. To calculate the covalent characters in an ionic bond, we have a rule called Fazan's rule. So Fazan's rule is a rule which is used to calculate the covalent characters in an ionic bond, since ionic bond is not completely ionic, right? So we have Fazan's rule which will gonna tell us the covalent characters in the ionic compound. Now see, Fazan's rule is qualitative rule. Very interesting, right? Qualitative rule. Which means it will not tell us about the quantity of covalent compound characters in an ionic bond. It will just tell us the characters, how much we will gonna compare the two compounds of ionic, what or which one is more covalent in nature or more ionic in nature. We'll just gonna compare it, right? We cannot know how much percentage of covalent characters are there in the ionic bond, but yeah, we can identify which one is more ionic or which one is more covalent. So this is qualitative rule. Fazan's rule will just gonna tell us the covalent characters in the ionic by comparing two ionic molecules, right? For example, solubility, right? We know that ionic compounds are more soluble in the water, right? So if I do talk about solubility, if if a compound will be more soluble, for example, let me write this here. If I have compound A and here I have compound B, this is more soluble, this is less soluble. This is more soluble means ionic characters here are more, right? This is less soluble, which means ionic characters are less, which means covalent characters are more here. Covalent characters more here, right? This I have just talked on the basis of solubility. You can talk about melting point, boiling point, since we know that melting and boiling point of ionic compound are greater, right? If a compound has more melting or boiling point, which means that is more ionic. And if a compound has less melting or boiling point, which means it is less ionic. Less ionic means more covalent, right? So this is how you're gonna compare two ionic compounds, and we're going to identify which one is more ionic and which one is more covalent, right? So Fazan rule is qualitative, not quantitative. In the next video, we will gonna look at some factors by what we can identify which one is more ionic, right? So in the next video, we're gonna discuss in very detail about Fazan's rule.